Hi everyone, welcome to part 5 of lecture 10. And as I said in the previous lecture, we will discover the conditional distributions in a special case, because we so far here we see how we can create the conditional distributions with under the situation, the conditions, the condition event is coming from the same event. But in this case, we will focus more special things. So instead of the conditioned event is coming from the same event, let's say we condition a random variable x on another y. So I hope that reminds you the joint probabilities, joint distributions, and think about the two events, and they will affect each other, and they will affect the final probabilities. Okay. So if this is the case, we will discover how we can create the conditional distributions. So if they are associated with the same experiment, as I said, and if we know that the value of y is some particular, the lowercase y, this provides some piece of information about the value of x, right? So I remember that we gave an example, like, let's say you went to the doctor and you gave some blood test, and there will be some things, right? Like the number of red cells, number of white cells, and they will affect the results. They will affect the diagnosis. So that means that two features, the x and y, will affect each other. So if that is the case, we can talk about this situation. So if x and y are discrete, we define the conditional probability mass function, because they are discrete, as this one. So the probability of the x given y evaluated in that lowercase x given y by the specializing the previous version of the conditional probability mass function of probability of x given e. So the e in this case coming from the same region. Do you remember that I draw something like that? We have some points and we define the event A. X is from this region and also conditioned event from this region. In this case, we have two different variables, but they will affect each other. So in this case, but the logic is same. So you can follow the same logic, like the probability of x given y. So that will probability of x is equal to the lowercase x, so that the x will take some values, and y will take some values, and that is equal to the probability of intersection of that two events, and divided by the probability of y, the conditioned event. So that's mean actually the marginal PDF of a random variable will be scale up the conditioned event. Okay, because remember that is the marginal PDF of the x, and we will scale up that marginal PMF in this example, because they are discrete, with the conditioned event. Okay, so the logic is the same. And also, if the x and y are continuous, we can define the conditional probability death function, which is the analogous to discrete case. So instead of the marginal PMF, we will use the marginal PDF, and that will be scaled up with the conditioned event. Okay. And please note that the PDF, the conditional PDF, or the conditional PMF, is defined only for the y values where those are strictly positive, because if that's 0, that will be undefined. Okay, you can check also the conditional PMF and PDF are legitimate by applying the probability axioms. Okay, so the probability of x given y and the PDF of the x given y are the function of the single variable. Why? Because one of them is fixed. Okay, so the fixed values will not affect the results of the function. So please remember that that is the function of only one variable. And their shapes, I mean, the unconditional situations, the marginal PDF and the conditional PDF are the same. They have the same shapes of the joint versions, but they will just scale up. Okay, so let me give you an example to make it more concrete. Assume that we have two random variable y and x, okay? And that is the joint PMF of the x and y. So that's PMF, the probability mass functions shows each individual probabilities, the probabilities for each possible pair of x and y, right? For example, which that height shows the probability for the x is 1 and y is 1. That is for the x is 1 and y is 2. And that is x is 1 and y is 3, right? So this all bars shows the corresponding probabilities. And that is actually the joint probability, joint PMF, joint probability mass function of x and y. Now, assume that, let's start from that one. Let's say we are given a condition which is y is equal to 3. So that means I just need to look at only this 3 bar, right? So I can safely disregard this remaining 6 bars because they are not satisfied with this condition because y is 2 and y is 1. But I'm given that y should be equal to 3, or for sure, not should, but y is equal to 3. So in this case, as we did in the previous lecture, the joint PMF will be scaled up by the conditional event. Okay, that means this probability will increase, that will be increased, and that will be increased. And the logic is the same. Please remember the same logic. Let's say, again, just to remind you, there are 6 different numbers, and I will ask you, I just randomly choose one of them, and I will ask you predict which number I choose. So your chance to correctly know that, to predict that, is 1/6. But if I tell you the number I choose is one of the numbers of 1 or 2 or 3, in this case, your prediction, your correct predictions will be 1/3, right? So I will scale up the unconditional one to the conditional one. The logic is the same. So if we are given this information, y is equal to 3, that means I will scale up the corresponding probabilities. Okay, but the pattern will be the same. Like in this case, in unconditional case, what is the highest probability is this one, right? For the x is 1 and y is 3. Same thing will be here. The highest one, this one, for the x is 1 and y is 3. And the middle one will be that one. The x1 is 2 and y is, x is 2 and y is 3. And the smallest one will be, again, this one for the y is 3 and x is 3. So the pattern is same, okay? Pattern is same, but I just scale up the probabilities. Or the condition can be y is equal to 2, and in this case, I will look at these guys, right? And also I will scale up this probabilities. The pattern will be the same, this one and this one, but that the magnitude of that probabilities will be greater. Okay, so the pattern will be same, but just I will scale up, and the same things for this one. If you consider the continuous case, that will be same, right? So let's say I will be given x is equal to 0. So that's mean I know that the x is equal to 0, right? So in this case, I can create that plane and I can follow this line, okay? And I can calculate the area under that line that will give me the conditional PDF for the continuous case. So that is the logic. So I will fix one of the variable and I will interest what happens after fixing that variable, okay? And that will give me the corresponding conditional probability. If so, the whole region is the joint PDF, right? So that will give us the any values. Like, let's say the x in x will take to this region, and the y is take from this one to this one, right? So I can just calculate the volume under the region, and that will give me the probability of x will be within this region and y will be within this region. So that is the joint PDF. In this case, the x is fixed, and I know that, and that information given to me. So I can create that plane, or I can just think that plane, and I can calculate the corresponding probabilities for the other variable while x is fixed. Okay, so that is the logic of the continuous case. So the conditional PMF, the probability mass function, or PDF, can be used to calculate the conditional probabilities, the conditional expectation and the conditional variances, just as we used in unconditional PMF or PDF to calculate the probabilities, expectation or variances. How? So let's say the probability of x that takes the values in A, given that y, which is evaluated in that lowercase y. So if I want to calculate that probability for the discrete case, I should calculate that summation, right? So that is the joint distributions. X will be in A and y will be fixed. If I fix the y and look at all possible x values within A, and if I sum up them, that will give me the corresponding probabilities, that conditional probabilities. And the same thing for the continuous case. Again, the y will be fixed, and I will check for that fixed values, what is the x values, what is the all possible x values within that set of A. And if I integrate that joint distribution, conditional distributions for the all possible x, that will give me the conditional probabilities. Okay. So okay, before going to the show of you how to calculate the expected value and the variances, let me summarize that one. So in the previous lecture, we look at the conditional distributions, right? So basically, so what is the distribution? Distribution shows that we can track all possible probabilities. We can calculate the probabilities for a random variable for any kind of, or the values, right? So the distributions will help us to calculate those kind of things. In this lecture, we have discovered how we can make the same calculations if we are given some piece of information, and that piece of information defined as a conditioned event. Okay. In the previous part, we have seen that the conditioned event is coming from the same set. And we see that how we can calculate that one. But now the logic is same, but instead of, so rather than the same event, assume that we have a different variable, y. But y will affect or affects the x1. So if that is the case, we look for how we can create the conditional distribution and how we can use that one. Okay? To show that, we show that in a such way, the probability of x within a set, given that y is equal to some specific, some particular value. Okay, so that is the given. And that is the thing we will calculate. Okay. For the discrete case, we will fix the y values. Okay, and that will give me. So we will fix the y values and we will check the all possible x values for that fixed y values. And the summation of them will give me that conditional probability for the discrete case, and the integration of this one will give me the conditional probability for the continuous case. Okay. Which is similar to the joint distributions. Instead, we are given the fixed value of one of the variable. Okay. So the conditional expected value of x given y, which is equal to some particular value, can be calculated using the conditional PMF or the PDF. So the expected value of x under the condition y is equal to some particular y, so which is equal to, for the discrete case, x time corresponding conditional PMF, okay? And for the discrete case, the expected value of x given y is equal to some particular value is the x times corresponding PDF, the conditional PDF of the conditional PDF of x. And we need to integrate this term for all possible x values. Then that is valid for the continuous random variable. Okay. So, and let me remind you something. So when I fix that the x values and I calculate the corresponding probabilities for all possible pairs like x0 and all possible y values, that is the marginal PDF of x. Okay, actually I'm talking about the marginal PDF of x here. Okay, so okay, and we can calculate that expected values in this way. Similarly, we can also calculate the variance of the x under some condition, like the variance of x given y is equal to some particular y values for the discrete case, which is equal to the summation of x minus the expected value of x given y is equal to some particular y values, the square. So, and weight them with the corresponding conditional probability. Okay, and for the continuous case, the logic is the same. The integration of x minus expected value of x given y is equal to some particular value of y, the square, and the corresponding PDF, the conditional PDF. Okay. So please try to understand the logic. Okay. Okay, so just disregard the probabilities. If I give you some constant values, some sure values, okay, how you can calculate the variance? You can simply say that like x minus, or let's say, yeah, x1 minus mu square plus x2 minus mu square, etc. Right? So you can calculate the variance like that. If I give you some probabilities, so you, instead of mu, in this case, you have to use the expected value of x, right? Because that is not for sure. That's why we expect that. Okay, expect that. And our expectation is based on our the probabilities, right? That's why we have to weight them with the corresponding probability, right? That's why we use the expected value when we talk about the probabilities. If I give you some condition, so the expected value in this case will change based on that condition, okay? So actually, this is what we are doing here. The logic is the same. Just make them more concrete, okay? Think about that, these things. And actually, we are doing the same thing, but instead of normal math, okay, we are just considering the probabilities and some conditioned events, but the logic and the way we follow is the same. Okay, so that is how we can calculate the variance under some condition. So, and also the differences between the previous part is the y and x is just the different random variables. They affect each other. If you don't want to calculate the variance with this way, you can simply use that formulation, right? X squared. But now we have the conditioned event. That's why we first need to calculate the expected, the second moment, and then okay. So, or you can use that one to calculate the variance. Okay, so that is, and how we can calculate the expected values, the x time, the corresponding probabilities, right? So if you want to calculate the expected value of x squared here, instead of x, we just put x squared and the corresponding probabilities. Okay, so that is how we can calculate the variance. You can use this way or this way. It depends on you. Okay, so that is the end of part 5, and the part 6, we will make it more concrete by solving an example, and I will see you in next part.